Good afternoon, everyone. We are the team members of the next team, and we are from Białystok University of Technology. We were introduced by the chairman, so our topic is Universal Robotic Arm System with interchangeable end effectors and advanced human rover interface. Let's start with the development of rovers at Białystok University of Technology. Right now we have built a 6th rover. 5 previous ones are listed in this slide. Magma 2, Hyperion 2. And next rovers were competing in University Rover Challenge. 3 of them won this competition, and one of the things they have in common is use of robotic arm to perform certain tasks at University Rover Challenge. And we were trying to make the best robotic arm possible, and then try to control it in the way that is more user-friendly and easy for operator. Moving on to robotics arm design, Michael.
The robotic arm mounted on the Mars rover analog, who participating in Universal Rover Challenge and European Rover Challenge, has to perform number of tasks. The basic tasks for a robotic arm is grabbing and moving objects using switches and valves. At the right hand side we can see a red rover. At the left side we can see joints of robotic arm. At URC 2016, it was used in 2 tasks. Astronaut assistance was the first one. We can see the photo from this task at the left-hand side. In this task, rover need to lift objects, in example, hammers or screwdrivers, put them into a basket, and then bring to the correct astronaut. Equipment servicing task was the second task with robotic arm mounted on rover. At first, rover attached a tow rope to the track. At the top of the track, canister with fuel was stood. Then bring it close to the panel, and next set the appropriate buttons, and finally poured fuel from the canister to the tank. The first degree of freedom is turntable. After URC 2015, it has been modified to URC 2015. At URC 2016, it was built from zero with completely new ideas. The first turntable on the left-hand side is built on polymer bearing for rotary tables from company IGUS. At ERC, which can be seen on the photo, turntable design is similar, but other IGUS bearing was used. That bearing almost completely eliminate the transverse loads. Life of the engines was increased significantly. The latest generation of turntables, we can see it on the photo, was built to eliminate transverse loads and interior of robotic arm. That was achieved by moving the motor axis outside of rotation axis of robotic arm turntable. The torque is transmitted via toothed belt, selection of gear, increased ratio, and improved control of rotate. And the second joint of robotic arm uses a worm gear, which gives a large capacity and self-locking. The robotic arm of Red Rover is made of carbon fiber plates. Transfer of motor for third and 4th joint is very important. In the #next rover occurred 2 generations of robotic arms. The first, from the left hand side, was a lot of small parts which transmit the rotation to the encoders. This solution was simplified in the second version. Unfortunately, this is still not improving principles of construction, which that the drive shaft is a structural element. It caused very fast wearing out of the engines. In Red Rover, the whole concept of transfer drive unit was changed, and engines are no longer structural parts. To achieve this, doubled bar bearing was used. Use of encoder and potentiometers is still possible with using 3D printed parts. Rotation of the actuator is the last joint. Thanks to rotary coupling, an infinite rotation is possible to perform. Exactly like in previous units, doubled ball bearing was used. This makes easier work of mechanism and protect them from transverse loads. The robotic arms is able to mount on it a lot of different end effectors. The robotic arm is also able to collect soil by using dig effector. We can see this effector on the right-hand side. This solution with dedicated gripper was used in ERC 2015 and 2016. Finally, to the duty at the competition, the team decided to use a gripper with 3D printed fingers. The solution used in robotic arm are an effect of several years of experience. It proved to be a good and robotic arm doing its takes correct and reliably. By using encoders or potentiometers as rotation sensor, inverse kinematics has been implemented. Good design of robotic arm in conjunction with Phantom offers great scope for further testings and allows to find a lot of uses for this structure.
Thank you. Many of the teams use joystick to control its robotic arm. It's a very reliable and simple way to do so, but it lacks some of the accuracy and ease of use when it comes to first comer to operation with this robotic arm. Our solution uses a Phantom device, a kinematic twin of a rover manipulator that allows easy control over its arm. It is made of PVC foam. The dimensions of this device is adjusted to fit the kinematics need of resemblance between robotic arm and Phantom. It uses also Eagles bearings that allow smooth and unjutted movement. It's light, durable, and resilient. For electronics part, we decided to use Intel Edison microcomputer. It unfortunately lacked serial port needed to control rover, so we designed a shield that eliminated that problem. And for rotation sensors, we decided to use potentiometers. Then we calculated some simple kinematics that allowed us to gain access to information about global position in a Cartesian system. To do so, we have made some calculations using David-Hattenberg notation, then transformation matrix has been made with a global transformation matrix of point P meaning the end effector. And the most important one is the fourth column that has coordinates X, Y, and Z inside it. Knowing the exact position, we send it to rover, where it has to be translated to angles on of different joints. And to do so, we had to perform also inverse kinematics calculation with each angle set in that manner, with the formulas. And afterwards, we made some trials, some tests to check if our solution works the way it's supposed to. So we first tried switching of switch, one of the parts of the astronaut assistance task. It looks like this. I hope it will play. Just a second. Let's try. Let's go. The computer is kind of slow, unfortunately. Let's give it a couple of seconds. Oh. Oh. And as you can see here, an operator is given orders to our robotic arm using Phantom device. It was before PID regulator was adjusted, so some of the angles may not be correctly reflected. We readjusted that, but during this trial, as you can see, switching is very simple. Just wave of hands and switch is turned down. We've measured time after the adjustments and operation time on 5 trials using Phantom in joint coordinate system are very similar to times used when we used joystick and the ordinary way of doing so, and Phantom using XYZ coordinate system is also comparable. Second trial, precision trial, we've marked a circle, and the operator's task was to put the marker as close to the center of the circle as possible, and and do it as quick as possible. Many of the attempts weren't successful, but those successful ones show that doing so is very quick, using Phantom with in joint coordinate mode, and doing so with joystick is very long and sometimes lacks a lot of precision. Trajectory quality was measured using, was observed using comparison of frames from a movie taken during this trial. As you can see here, those two frames are set on one on another, and this is the initial state of the movement. This is the final state of the movement, and those rectangles show the area of movement of the end effector. It's very narrow, so the recreation of movement is was quite accurate. This movie shows the trial. Oh, please. We also measured trajectory on rotary sensors and then recalculate the whole trajectory. This blue line shows trajectory of the TCP point of Phantom, and the orange one shows trajectory of the manipulator TCP point. As you can see, they are quite similar on those two 3D graphs, and we believe it's efficient enough to use it during competition. Moving on to the conclusion, redesign of robotic arm has increased its durability, resilience, and lifespan. Its use of carbon fiber plates has decreased weight while maintaining its strength. Phantom device can significantly reduce time needed to perform certain operations, and it eases use of the robotic arm. And it met with operators quite warm welcome, and so they decided to use it during University Rover Challenge 2017. Just let me mention our sponsors, grant giver and Ministry of Science and Higher Education in a program, The Best from the Best. And sponsors are our university that supported our efforts during the whole project. Thank you for your attention.
We now have a couple minutes for questions, if anyone has any.
Yes?
Two. Can you tell me roughly what the maximum tip loads are that it could fly? That's the first question. And the second, when you were doing your manipulation with the Phantom one, if you had a payload on the tip, did you also put a payload on the tip of the Phantom?
So starting with the second question, we didn't payload the Phantom because it's only pointing the point of the interest for a manipulator. It doesn't have haptic feedback between one another. This will be developed in the future. This will be my PhD thesis, actually. And with the first question, the payload on the end effector applied varies between 5 and 6 kilograms, and without much concern, but we haven't tried much more. It exceeded our needs, so we didn't want to break it down.